Hi everyone, this is just a short video detailing how can we use our properties of logarithms to help us differentiate some more complex functions. When I talk about more complex, I'm talking about something where you would have to apply many of the rules we learned. So for example, if f of x equals x to the eighth cosine cubed x over the square root of x minus 1, you can look at that function and see right away, well, there's product rule, there's quotient rule, we would have to apply that. And then within the product and quotient rule, we would also need to apply some chain rule for the cosine cubed x, for the square root of x minus 1. And as you can imagine, when we have to apply all three properties, it can get very tedious and can take a while to work through. So one of the things we can do is actually look at our rules for logarithms. So let's do a quick recall. If I had ln, when I say recall, I'm recalling back to, say, pre-calc 1 or your college algebra course. So suppose I had ln of a squared b to the third over c to the fourth. Do you remember how we could expand logarithms? We could expand logarithms using some pretty basic properties. One of them states, well, if you have two variables multiplied together, and you have to take the natural log of those two variables multiplied together, such as a squared times b squared, you can separate them as ln of a squared plus ln of b cubed. But then if you're dividing by another variable, that would be minus ln of c to the fourth. So if you recall your basic log property, log of xy is ln of x plus ln of y, and ln of x over y equals ln of x minus ln of y. Now, another property comes from the exponent. If you have ln of x to the fourth, if you recall, you can move that fourth out front, and it's 4 times ln x. So again, these properties are also reviewed in Chapter 1 of your calculus book if you want to take a look back at them, but you also learn them in college algebra or pre-calculus. So, understanding that, this would then become 2 ln A minus 3 ln plus 3, ln B minus 4 ln C. All right, so there's our quick little recall. So how does that help us? Well, let's go back to our original problem. F of x equaling x to the eighth cosine cubed x all over the square root of x minus 1. Now I'm going to make one little change in this particular function. In that, to understand a little better, I'm just going to label it as y equals. You can keep the f of x notation. Use whatever notation you'd like. You also learned when doing logarithmic, when learning about logs, again, in pre-calc or college algebra, that you can take the log of one side, ln y, as long as you do the same thing to the other side of the equation. So we keep our equation balanced in that if you take the ln of one side, it's the same as taking the ln of the other side. Now in doing that, I can expand the right-hand side. So using those properties, I'll do this one out step by step so you can remember the properties. I'm going to take the whole, hold on, not the 8, numerator this time, and subtract it by the ln of the denominator. And then I'm going to take that numerator, that first part, 1 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 I'm going to make one little switch here and state that the square root of x minus 1 is the same as x minus 1 to the 1/2 power. I'll then remove my powers. Remember, it's still ln y on the left. So I have 8 ln x plus 3 ln cosine x minus 1/2 ln of x minus 1. I've expanded this particular log out as far as I can go. Now that I've done that, remember what our goal is. We want to take the derivative. So let's go ahead and use implicit differentiation and take the derivative. In other words, I want to find dy dx. So let's start with dy dx of ln of y. Well, the natural log, the derivative of the natural log of y, of course, is 1 over y times dy dx from implicit differentiation. How about the natural log of 8 ln x? Well, that's just going to be 8, and then the derivative of ln x is simply 1 over x times, of course, dx. We don't need to write that. How about 3 times ln cosine x? Well, the 3, same thing, over cosine x, because the derivative of the natural log is 1 over. But then you have to apply your chain rule here. What is the derivative of cosine x? Negative sine x. So you're going to multiply by that. And then 1/2, 1 times 1 over x minus 1. Again, you need to apply your chain rule, but this time you're taking the derivative of x minus 1, and the derivative of x minus 1 is simply a 1. So I'm going to go ahead and clean this up a little bit. So what do I have? I still have 1 over y times dy dx, 8 over x. This minus sign is going to come out front. I can write sine x over cosine x as tan x. Just keeps it a little bit neater. And when I clean this up, I end up with 1 over, what's that, 2x minus 2. Okay? Now we're not there. What are we doing? We want to find dy dx. So I need to multiply both sides of the equation by y. Okay? So dy dx, 8 over x minus 3 tan x minus 1 over 2x minus 2 times y. Well, what was y? And there's your y. Y, of course, is equal to your original function, which is x to the 8th cosine cubed times x to the 8th cosine cubed x over the square root of x minus 1. That is complete. So if you know your log properties, you don't need to distribute it. It's just going to be as messy as if you try to distribute, so you can leave it in the unsimplified form like that. I mean, there are little things I do. Obviously, when you see things like sine over cosine, you can rewrite that as an x and so on. But that does it. And that shows you how you can use expansion. If you want, go ahead and try to solve this problem using all of those rules. You will get a slightly different version of the answer, and my guess is it'll take you a little bit longer to get there. There are other examples. If you go to your textbook, whether you have your textbook a hard copy or you have it online, if you look at page 214 of your textbook and look at example 8, you see another example of logarithmic differentiation. Thank you.